we are coming towards the end of our course. In this lecture, we will be studying some constructions of hash functions, and at the beginning we will look at a general strategy of constructing hash functions. Now, the main problem over here is that we have a set X on which we would like to define a function which will take values to another set Y. This set Y is relatively small, or just write finite, but this set is potentially infinite. Now, we will assume that we have some access to functions which are called compression functions, that is functions from finite set, a large finite set to a smaller finite set. So, and we will call that function compress. Now, the trouble is that this compress cannot work always, because as I said, potentially we can have the values of x larger than any previously determined value. So, we would like to build up a strategy so that we can scale up this function to any length and any length of x, and with the security conditions intact. So, what we will be doing is that we will say that, okay, suppose compress is a good function, suppose compress is collision resistant, second pre-image resistant, pre-image resistant, and like that, and we would like to somehow use compress to build up a bigger function, a function on a bigger space which will have the same security properties as compress. So, that is our goal. So, here we see that we have compress from 0 1 to m plus t going to 0 1 to m, and we would like to have an h which is starting from I equal to m plus t plus 1. So, 1 more than m plus t and to infinity. So, I write our goal here. We need not write the set notation around infinity, that is a misprint, just infinity, and I m plus t plus 1 0 1 raised to the power I going to 0 1 to L, where L is something like L may be L may be m, or L may be smaller than m. Possibly L is equal to m. Now, our strategy has a pre-processing step. So, once we get x as the input, we know that we have compress. So, let me write down compress on the blackboard. So, compress is equal to 0 1 m plus t goes from 0 1 m plus t to 0 1 m, and here x is an element in x such that the length of x is something greater than or equal to m plus t plus 1. Now, we can think of x as a sequence of symbols like this x1, x2 and x3, xi plus 1 and so on up to let us say ultimately some xk. So, first we would like to split up x into some small parts because we want to use compress. So, we would like to split up like this some segments of length t, then again another segment of length t and so on. But there is a problem. At the end it is possible that the end of x will not match with a multiple of t. Therefore, we will have to put some extra bits which will be called padding of x. So, there will be a public algorithm of padding that we will put on after x, so that it will be a multiple of t. Suppose after doing that we have got a string like this which is y, which is a multiple of t. Now, at this point I will clarify one symbol. If we say write something like this, this means concatenation. All right. So, for example, if y1 is equal to 0 1 0 0, y2 is 1 0 0 1, y3 is 1 1 1 1, then y concatenation y1, y2, y3 will give me 0 1 0 0, 1 0 0 1, 1 1 1 1. This is concatenation. So, we are splitting up y into substrings of t. Now, let us see how the algorithm goes. We will have a publicly available initial vector which we denote by iv. So, we will put that iv over here and the iv will be of length m. So, let me remove this portion. Yes. So, we will start from a vector 0 which will be initiated by iv. It is called an initial vector. This will be available to everybody. So, I give this initial vector and the length of iv in bits will be m. So, I put iv over there and then after that z1 will be computed in this way. I will apply compress over z0 concatenated with y1. Let me draw y1 over here, the y over here. So, y is y1 concat y2, y3 and so on up to let us say yk, and as we have seen compress is a function from 0 1 to the power m to 0 1. So, m plus t to 0 1 to the power m, then this string is of length m and this string of length t, therefore, the concatenation is of length m plus t. So, I can apply compress on it, and after I apply compress I will get z1 which is of length m, and after that we will go on recursively, we will apply compress on z1 concat y2. So, we are one by one we are catching the initial segments of y, now we catch y2 and then we will write z2 and then we will write compress z2 concat with y3 and write z3, and predictably we will go like this, ultimately we will come to some yr, let us say that is the last segment. So, yr, the previous value of compress zr minus 1 concat yr, and we are getting zr, and after that there is a step which we may need or may not need, that is depending on the size of the input output set. We may, what we get over here is a string of length m, we can map it to something, it may be basically anything, but possibly L will be less than m or equal with some map, and we will get this Hx equal to some g of z sub r, and we will take it as our hash value. The important point here is to note that we are using recursively the compress function to go into a chain. What we have to prove or what we want to happen if this has to be a secure hash function is that when we go into a chain like this, the properties of pre-image resistant, second pre-image resistance and collision resistance should not be disturbed, they should remain intact. Based on this strategy, we have a particular construction which is called Merkle-Damgard construction. I will discuss the steps of Merkle-Damgard construction now. In the case of Merkle-Damgard construction, we have a compress function from 0 1 raised to the power m plus t to 0 1 raised to the power m, and we assume that this function is collision resistant, and we also assume that t is greater than or equal to 1, and we would like to construct a function on x which is union of 0 1 raised to the power I running from m plus t plus 1 to infinity. Now, the construction technique is slightly different from the general iterative construction. Here, instead of breaking up into segments of t, we will break up the padded value of x into segments of t minus 1. So, we first have to determine that how much we will we have to pad and what will be the pad. So, in the first step we compute the length of x and we store it in n. This is the length, and then what we do is that we divide n by t minus 1 and take the ceiling of the result. So, what we will get is something like this. Suppose length of x is up to this and this is So, let us suppose this is n and this is t minus 1. So, we will, when we are dividing, we will come up to this some integer multiple times of t minus 1, and at the end we will have a position here which is the remainder, this whatever numbers are, whatever many points are over here, that is the remainder, that is called d. Now wait a moment, this is, let us call this a remainder, but what we are doing is that we are dividing n by t minus 1 and then taking the ceiling, and suppose this is equal to k, then if I take k into t minus 1, I will go up to this point, I will overshoot the length of x. You can check that with small numbers, and I am interested in this portion, and that is what we compute over here, k into t minus 1 minus n. If I do this, I will get this portion, and that is what I call d, and that is what we have to pad. So, then we go into a loop I equal to 1 to k minus 1, and then I put xi equal to yi up to k minus 1. So, it is not k, up to this it will be k minus 1 into t minus 1, and from here to the end will be k into t minus 1. So, what we are doing is that up to k minus 1 I am taking yi equal to xi, I am just mapping them, and at the end at k I am padding by d 0 values. So, I will be putting d zeros over here. So, that is the padding algorithm for Merkle-Damgard construction, and after that at y we will have another extra segment, that is yk plus 1, that will be the binary representation of d. I will put the binary representation d at the end. So, for x I will have segments of y, y1, y2 dot dot up to yk, and then at the end I will have another segment which is the binary representation of d. All right. Now, after this we go into the computation of the values. Please remember that yi's are of length t minus 1. So, I have to do a extra padding. So, in the initial case I will put the initial value will be 0 concatenated m plus 1 times and then y1. So, this whole thing is m plus t, and my compress function works for, wait a moment, yes, this is m plus 1 and this is t minus 1. So, you will have m plus t, my compress function is from m plus t to m, I will get z1, z1 is of length m, I will wait a moment, sorry, it is like this, I will construct this, this is z1 is of length m plus t. So, I have got a string of length m plus t here, and then I will apply compress over z1 to get g1, and g1 is of length m. Now, after I have got g1, I go into a loop from I equal to 1 to k. Here I will put I will concatenate 3 segments. I will have gi is of length m, then I will have a buffer kind of thing with 1 bit, that is 1, concatenate with 1, and here I will put y I plus 1. I know that this length is t minus 1, this is 1. So, this is total length is t and this length is m. So, total length of this each z I plus 1 is m plus t, and I will apply compress on this, I will get g I plus 1. We will keep on doing this, and at the end I will put g k plus 1 as h x. At the end here I will come up to z k plus 1. We will also use y k plus 1 here, and we will return x. But this algorithm is Merkle-Damgard, this construction is Merkle-Damgard construction, but there is another variation of this, because we will note that here we are splitting up the inputs in segments of t minus 1. We have to assume that t is greater than or equal to 2. If t is equal to 1, then we do not know what to do with this, because then we are splitting up the input sequence as a segment of length 0. We can't do that. So, for that we have another algorithm, this is this one. So, here t is equal to 1. So, the compressed function is a function from m plus 1 to 0 1 raised to the power m plus 1 to 0 1 raised to the power m, and we are taking the length of x as n, and there is a particular way of concatenating and finding out y. First we will put 2 1s, then concat with fx1, fx2 and so on, where f0 is 0 and f1 is 0 1. We will have to put like this, and once I do this, after that we will consider y as bitwise. So, we will have a finite sequence of 0 1s of y, and then we will construct bitwise, and after we do that we will have an initial vector of all 0 of length m, and we will concat y1 to it. Y1 is just of length 1. So, I can use compress here, because compress is a function going from 0 1 raised to the power m plus 1 to 0 1 raised to the power m, and then we go into the loop, and ultimately we will come to the hash value. So, we have checked some constructions, general constructions of hash functions, and this is more or less that we will be doing in hash functions. In the next lecture we will discuss some problems on hash functions and some other problems from the previous lectures, but let us stop for the time being. Thank you.